So let's talk about the Lee phenomenon a little bit, and we'll start with a review of how to back calculate. Let's assume that we went out and took a sample of fish, and the particular data that I'm going to show you today were fish that I took in summer of 1999, specifically August of 1999, and all the fish were measured and their otoliths removed. And all the otoliths were then aged and measured on the computer for back calculation. And so here is a table of the results from that sample. So the first thing we want to ask is how many fish did we have? And if you look over here, we've got the year class. And for each year class, we've got how many we caught from that year class in our sample. So if you sum those all up, you get 57. Double check my math for me. And so we had 57 fish. We see that they ranged in age from age 1 to age 5. There were no age 0 fish. And what you see here is a summary of the mean back calculated length at age for each age class. So let's review how we get that back calculated length at age. So first, let's look at the 1998 year class and make sure that we understand when the fish were spawned and how we do these ages. So the 1998 year class was born during the spring of 1998. That's why they're the 1998 year class. On January 1st, 1999, they all turned 1 year old. Now, of course, they weren't exactly 12 months old. They were probably born in April or May of 1998. But like we said, all fish have the same birthday. So on January 1, they all turned 1 year old. And then we caught them in August of 1999. And if you look at the table here, you see we've got the 1998 year class, and you see that we have their length at age 1, but not any other ages because they were only 1 year old when we caught them. And in a similar way, you can look at 1997, and so that's the 1997 year class. So they were born during the spring of 1997. On January 1, 1998, they all turned 1 year old. On January 1, 1999, they all turned 2 years old. And then in August of 1999, we caught them, and they were 2 years old. And so study this table and make sure you understand how all these year classes work and how they relate to the time which we caught them. We caught them all at the same time, which was August of 1999. And again, this table summarizes the back calculated length at age for each year class. And this is an average across all fish. So for example, if we look at the 1996 year class, we caught 11 of them. And on average, these fish were 160 millimeters when they were 1 year old. They were 219 millimeters when they were 2 years old. And when they turned 3 years old, they were, on average, 300 millimeters. So how do we get these back calculated lengths? Well, remember that we've got a very simple formula using the dimensions of the scale and the length that the fish was when it was captured to determine the length at age. And also remember that for otoliths, we can use the simple form of this formula. But if we were using scales, we would need a correction factor called A. But we're not doing scales, so we can use the simple equation. And again, L sub AI is how long was the fish at a previous age. That's what we're looking for. That's what we're going to solve for. S sub AI was how long was the scale at that previous age. Now I'm saying scale here. Of course we're using odorless, but the formula has an S in it for scale, so we'll just say scale when we mean otolith. And so how do we get, how do we know how long that scale was a few years ago? Well, we just get that by measuring the proper annulus. The annulus was formed when the fish had its birthday. Then we also need to know how long was the scale when we captured the fish. Well, again, we can measure that, and this time we're going to measure the entire scale because that's how big it was when we caught it, because we just caught the fish. Now, how do we measure the scale? How do we get these two values? Well, that's done in several ways, but the easiest is with a computer. We take a picture of the otolith, and then there's simple software that allows us to measure these distances, and we can plug them into the formula. Finally, we need the length at capture, and that's very easy because we captured the fish and we put them on a bump board and we measured them. So we have our three values that we can plug in to get the length at any previous age. So let's do an example here. This is a fish that was 240 millimeters long when we caught it, and you can see it's 2 years old. There's annulus 1, there's annulus 2, and then we caught it in the summer. So now, just as a mental exercise, we took the sample in August of 1999. So in what year was this fish born? Well, if the fish was 2 years old in August of 1999, it must have been born in spring of 1997. So it's in this 1997 age class. Born in spring 1997, January 1, 1998, it turned 1 year old. January 1, 1999, it turned 2 years old. And then we caught it in August of 1999. And so how long was the fish when we captured it? Well, that's L sub C, and we already know that. We put the fish on a bump board. So the first value is easy to get just by measuring the fish. And if we go back to our formula, how long was the fish at capture? L sub C. We just plug that in here, and we see that it goes right there. The fish was 240 millimeters. How long was the scale at capture? That's the length of the scale. That's S sub C. And again, we take this picture. We can use some software to measure these distances, and we measure this distance right here from the focus to the edge of the scale. And just for our example, let's say that that was 100 pixels. Now, it does not matter what units you use. You can calibrate this and you can measure it actually in millimeters or micrometers, but you don't have to, because it's a relative amount. It's a relative measurement from each annulus to the end of the scale. And so it doesn't matter as long as they're always done in the same units. So on the computer, we can just measure in pixels, and it's very simple. So let's assume that that distance is 100 pixels. So that's S sub C. So we plug that in to the formula, and you see that there's your 100, And of course, this is still already in there. That was the length of the fish when we captured it. So now we want to know how long was the fish at age 1. So we need to know how long was the scale at age 1. Well, that is just the distance from the focus to the first annulus. But here it's important that you measure it on that same axis that you measured the scale length. You don't want to come and measure here. You don't want to come and measure here. That would be disproportionate, so don't do that. You want this distance right here because that's on the same axis that we measured the scale length. And let's just say that that is 65 pixels. Now remember that this annulus, we're going to say that it was formed on January 1 of 1998. Fish was born in spring of 1997. It grew through all of 1997, and then in the winter on January 1 of 1998, it turned 1 and it laid down this annulus. So we are assuming that the annulus is laid down in the winter right when it has its birthday. That may not be strictly true, but it's pretty close for most of the species we work with, and as long as we do it consistently, we should get fairly consistent numbers that we can compare across age classes. So now we know all three values. We know that the scale length when the fish turned 1 year old is 65, which we plug in. And so we plug and chug, and you see that the fish was 156 millimeters long on its first birthday. And basically, if we repeat that, we can back calculate the length at age for all ages for all fish. Now, I want to point something out. If we go back to our table, you see that this fish was 156 millimeters. But if we look for that year class, age 1 length, it says 170 millimeters. Why the discrepancy? Well, remember that we had 18 fish from that age class in this sample. What I showed you previously was just a single fish. We have to repeat those measurements for the other 17 fish from this age class. And then we take the average age 1 length across all 18 fish, and that's how we get the number that we have here in this table. Okay? So the fish that we just measured previously, that was a smaller fish from this year class. It was only 156 millimeters, but when we took it, all the other 17, and then we took the average across all of those fish, the average size at age 1 was 170 millimeters. And so now let's repeat that for the same fish, and let's see how long was that fish was at age 2. So of course now we need this distance. Again, along the same axis that we've been doing. And we measure that on the computer and we see that it is 90 pixels long. And again, remember that that represents how long the fish was on January 1 of 1999, the day this fish turned 2 years old. Okay, so it's your turn now. You know all the values you need. You can pause this, you can go back and look them up if you didn't write them down. But I'm going to wait for a second and I'm going to give you a chance to figure out how long was this fish at age 2. Okay, did you get it? Let's see the answer. So if the scale length was 90 pixels in that second annulus, and we already know we use the same scale length, and we use the same length at capture, so that fish was 216 millimeters when it turned 2. And so now we're going to repeat that for all 57 fish in our sample, and we're going to measure all annuli for all otoliths, and we're going to do these calculations for all ages for all fish, and then take the mean within each age class and within each year, and that's how we get this table. And so again, by that same logic that we had, that this is the average length of each age class on January 1 of each year. Remember, the fish that we worked up was 240 millimeters when we caught it in August of 1999. And when we did the calculation, it was only 216 millimeters on January 1 of 1999. And so the table is telling us the average size on January 1 for each year. And then all those fish grew a little bit during the summer of 1999 before we caught them. So this clear area here represents that growth since 1999. And for this fish, I know that growth was 24 millimeters. And so maybe you can sit and think for a second, how do I know that the fish grew 24 millimeters this year? You think on that. At any rate, again, once I do that for all fish and take the average, what I have in this table is the mean length on January 1 for each of these age classes. And the mean length for each age class when we captured them is going to be slightly bigger because they all grew. But we wanted to be consistent for this table, and so we have the mean length at January 1. Okay, so that is a review of how to do back calculations, and next we're going to talk about the Lee phenomenon. All right, so now that we have reviewed how to do back calculating, let's go and look again at our table. And we see the results of doing the back calculation for each year class. So now the question that we can address is, so what is the Lee phenomenon? And so let's talk about the Lee phenomenon by looking at this table. Let me go ahead and get a pen here. So let's look at the back calculated length at age for a particular age group. So let's look at the back calculated lengths at age 1, and let's look at that for each year class. So we have these 5 different year classes. And look what happens as you go from the youngest year class to the oldest year class. Look at how the average back calculated length gets smaller as the year class gets older. And this happens for all ages. If you look at age 2, you see that the back calculated lengths for the older fish at age 2 are less than for the younger fish. All right? And so this happens pretty consistently when doing back calculations, and that's what the Lee phenomenon is. The Lee phenomenon is when back calculated lengths get shorter for older year classes. And so that begs an interesting question. Well, why? If this happens consistently, why does that happen? And the most common explanation is that only slowly growing fish live to older ages. And so when you have those older year classes are represented disproportionately by the slowest growers. And so when you do back calculating lengths for the older fish, those back calculated lengths are shorter at every age because those fish were shorter at every age. Those fish grow slower. That's why those fish were able to live to the older ages. And that is the most common way to describe the Lee phenomenon. Well, let's investigate this a little further, because why do the slower growing fish live longer than the faster growing fish? Or if those older year classes are made up disproportionately of slow growing fish, well, why is that? Well, let's take a look at a theoretical example here. Here's my theoretical population, year 1. So this is a cohort, this is a year class on their first birthday, and they're all pretty small. But you see we have a range in sizes. We've got some slow growers that are small, see them? And we've got some medium growers, and we've got some fast growers. We have equal numbers of each of those right now. But as is typical with any year class, you have a range from slow growing to fast growing. All right? So at this point, on their first birthday, the slow growing fish make up 33% of the population. So they're a third of the population. Now, what we're going to say is that those fast growing fish, those larger fish, are going to be the first ones taken out of the population. Well, why is that? Why are the biggest fish or the fastest growing fish the first ones to be removed from the population? And there are many reasons. The most common is that those fast growing fish are the first ones that recruit to the fishery. And so, for example, there might be a minimum length limit on these fish before you can take them out of the lake. And the fast-growing fish are going to be the ones that hit that minimum length limit first. And when they hit that minimum length limit, that's when they recruit to the fishery, and they have the potential to actually be removed from the lake. And so some of them are going to be removed. So as people remove fish from the lake, they're going to remove those fast growers disproportionately relative to the slow growers. This might be something in a commercial fishery. It might be that the fast-growing fish hit a commercially acceptable size sooner. And so the fish have to get to a particular size before it becomes economically feasible to harvest them. And those fast growers are going to be the first ones to hit that economical size. And so because of that, those fish get removed from the fishery. And so here we are, same population, but this is year 2 on their second birthday, and maybe you can tell, but the fish have all grown. So all the fish have grown some. And now we have more of these fish recruiting to the fishery. Of course, the biggest fish, they already recruited to the fishery. They're already vulnerable. Now you've got the medium growing fish have recruited to the fishery. But these slow-growing fish still have not gotten big enough to recruit to the fishery. And so here we just have a number of these fish get removed in this next year because they're big enough to be removed. And so here we've removed them, and you see that now that the slow-growing fish make up 50% of the population. Before they were a third of the population, now they're half of the population because those fast growers have been disproportionately removed. Well, same thing. Here now the remaining fish grow. This is year 3, and we see that all the fish have recruited to the fishery now. They're all big enough. And so we get a lot of fish being removed. Actually, I guess I modeled, now that I look at this, it looks like I modeled that these slow growers still have not recruited to the fishery. So although it's year 3, although they've grown, all these slow growers are still not big enough to take, at least, again, in this theoretical population. And so we have more of the medium growers and the fast growers removed. And now at this point, the slow-growing fish make up 64% of the population. So you see how those slow growers become a larger and larger percentage of this theoretical population. Well, if I were to sample this population today, and then I did back calculation on all those on their lengths, those lengths would be shorter because these are the slowest growers. So these fish actually were shorter at those earlier ages. We've removed the fast-growing fish. And so now, if you look at the table of the back calculated results, you can see that. You can see that as the year classes get older, the average length at any age seems to be a little bit smaller. And so this 1994 year class, there's only 2 of them that are still left around. They're probably slow-growing fish. These fish were, on average, only 150 millimeters when they were age 1. Now, if I went back in time to 1995, when those fish actually were age 1, this number would be a lot higher because a lot of those fast-growing fish would still be in the population. If you look at the 1998 year class, you see there's a lot of them still remaining. So a lot of those fast growers are still in the population, and that's why the average back calculated length at age 1 is higher. And as those fast growers get taken out, then that average back calculated length gets less and less. So that's the most common way to explain the Lee phenomenon. Now there are other ways you can explain this, and all these factors might be working simultaneously. Another common explanation for this is that as you eat and as you grow, you accumulate toxic metabolites. So one of the consequences of respiration, of taking food and breaking it down, is you create these toxic byproducts. And sometimes they're called free radicals. They're a type of molecule that oxidizes things readily, and they're very reactive, and they're toxic because they react with things in your cells. And so they react with cell membranes, and they react with DNA, and they break down those important molecules that are important, and they break down important structures that are essential for the functioning of the cell. So the more you eat, the longer you live, the more toxic you become, and your cells begin to break down. Now, you may have heard of things like antioxidants, and people suggest you should eat and drink more antioxidants. Well, this is what they're talking about. An antioxidant is going to neutralize those free radicals, because those free radicals are oxidants. They oxidize things. So an antioxidant will neutralize them, and so then they won't break down your cells. That's the theory anyway. So this is suggested to be one of the reasons that you age and that you eventually die, is the more you eat, the more you accumulate these free radicals, and the worse your cells become. And so if you're a slow grower, and if you eat less, then you tend to live longer. And we see that in fish populations, and we also see that in other vertebrate populations, like humans, that by restricting your calories, that can add years to your life. And so that's another reason why the fast-growing fish might be pulled out of the lake sooner than the slow-growing fish. Another thing that has to do with fish is, I don't have it on the slide, but I'll write it here, is aggressiveness. And wow, is this hard to write with a mouse? I'm just going to put aggressive. And so if you think about a lot of sport fish species, the fast-growing fish are often more aggressive. And that's often why they're growing fast because they are more aggressive toward prey. Also, they might have a higher metabolism, so they need to be more aggressive. It's kind of a chicken and the egg thing. But for whatever reason, if you're growing faster and you're more aggressive, well, that's going to make you recruit to the fishery sooner too, because you're much more likely to strike a lure, for example. And that's going to make you more likely to be pulled out by a fisherman. Also, if you're more aggressive, you might expose yourself more. And so you might expose yourself to other predators more. So that also might be an explanation for why fast growers are removed disproportionately. So here's our original population again. And we can ask ourselves, well, what if slow growth was a serious disadvantage? Because you can think of a lot of scenarios where slow growth would be a bad thing for a fish. For example, if you grow slowly, that means that you're going to be vulnerable to other predators much longer. And if you can grow fast, well, then you can get too big to eat and you're less vulnerable to the predators. And if you get big, then your mouth gets bigger, which means your gape gets bigger, which means you have more potential prey, for example. So getting big might be an advantage. If you get bigger, if you're a female, you can hold more eggs, you can have more offspring. That might be an advantage. Well, these factors all work simultaneously in a fish population. There are advantages and disadvantages to fast growth. And so it's possible in a certain situation that the disadvantage to slow growth outweighs the advantage to slow growth. And then you might get something like a reverse leaf phenomenon, where as you back calculate the lengths, the older age classes are actually larger. And that could happen, but that's not as common. More commonly, you do see that the disadvantage is with the fast growers, and they're removed from the population sooner. And so that's it for the leaf phenomenon and for back calculating. And I appreciate you listening to this. If you've got any questions, let me know. So have a good day.